Welcome to today's lesson. Today we are looking at proof of divisibility by mathematical induction. The question that we have right there says, prove that 7 raised to the nth power minus 1 is divisible by 6. So now, in mathematical induction, we must always know to say there are 3 steps that we must consider. So the first step being the basis step, the second step being the assumption step or the inductive step, and lastly you have the conclusion step where you must conclude your proof. So now, how do we go about this proof of divisibility? So the first thing that we do, we must let n to be equal to any integer that you might think of. So on this one you are not limited, provided they've given you conditions to say this is the type of integer that you must use. But if you don't have any conditions, you can use any integer. So in certain questions they will give you a condition to say you must this statement is confined to positive integers only, or any numbers that are greater than 1 and the like. So for this one, it's just free. So now, in this video, for this particular question, we are going to let n to be equal to 1, like that. We are letting n to be equal to 1. So now, after letting n to be equal to 1, meaning that wherever there is n in our statement, we must replace with a 1. So now, this will look like this. This will just be equal to 7. Where there is n, we are replacing with a 1. So this will be 7 raised to power 1 minus 1, like that. So now, 7 raised to power 1, these are unit indices. So any number raised to power 1 is that number itself. So now, this will just be equal to 7. 7 raised to power 1 is 7. So then 7 minus 1 will give you a 6. Now, if you check the answer that we've gotten after replacing n with an integer which is 1, you would find that if you divide this 6, the answer that we've gotten from this statement, by this 6, you will check to say it is truly divisible by what? By 6. So, and hence, you conclude to say the statement is true for n is equal to 1. That is it for the first step. You say it is true for n equals to 1, like that. Then we move on to the second step. Now for the second step, this is the assumption step or the inductive step. For this one, the first assumption that we are making, we are letting n. We want to assume, you assume if it is true, for n is equal to k. So meaning that wherever there is n in our statement here, we must replace with a k. So this is just equal to 7 raised to power k minus 1, like that. We keep this statement. We can call it as our equation 1, like that. Okay? Then if it is true for n is equal to k, meaning that we can also use this same assumption to also prove that it can be true for n is equal to k plus 1. Okay, so now what we are doing here, we must let n to be equal to k plus 1. We are letting n to be equal to k plus 1. So we are doing the same thing. Where there is n, we are replacing with a k plus 1. So now this will just be equal to 7 raised to power k plus 1 minus 1. We can call this one as our equation 2, like that. Alright, now, how do we conclude this? We conclude this by saying the last step should be the function of k plus 1 minus the function of k, like that. Which one is our function of k plus 1? When we talk of the function of k plus 1, we are simply talking about When we talk of the function of k plus 1, we are simply talking about the stage where we had replaced n with k plus 1, which is this one, the one we called our equation 2. So now this is what we are replacing on f of k plus 1 in brackets. So the statement is here, you have a 7 raised to power k plus 1 minus 1, and then this is minus, so we say minus. Now for the next statement, what we do, we say for f of k is where we had replaced the n with a k, which is our equation 1, like that. Now we must put it in brackets so that we separate this sign from the other statement, so that we can have so that we can distribute this negative sign into the 7k minus 1, which we called our equation 1, like that, because this is just there in the formula, it's not part of the f of k. So we do this so that we separate the two. Then in brackets you have the f of k, which is just 7k minus 1, like that, the one we had called as equation 1. So at this stage now, we should now be able to distribute this negative into what we have in the brackets. So the next step will look like this. You have a 7 raised to power k plus 1 minus 1, like that. Then negative times positive 7 raised to power k will give you a negative 7 raised to power k. Then this negative times the negative 1 here, negative times negative, you get a positive 1, like that. So now what happens here, if you were to look at this negative 1 and the positive 1, these are like terms, so automatically when you add up these, they will give you a 0, so you can cancel out from there, you can cancel them out from there. So what will remain is the function of 7 raised to power k plus 1 minus 7 raised to power k, like that. Okay, so now after we've done this, the next thing we must do is to separate this 7, because we have a k plus 1, it's a linear exponent right there, so we can separate the k and the 1. So what to do is this will look like this. You have a 7 raised to power 1 times 7 raised to power k minus this 7 raised to power k again. So what I will do here is you can put this one in brackets because these two are multiplying. So this is just 7 raised to power 1 is 7. So this is just 7. Then in brackets you have a 7 raised to power k minus 7 raised to power k, like that. So what we have here is this 7 here acts as the coefficient for this. So this looks like a scenario where you have, let's say, a 7a. Okay, so this 7 and that one, this 7 is acting like a coefficient of what you have in there. So this and that one can subtract. If you look at this one and this one are the same. So you can have a 7a, for instance, minus a. 7a minus a is 6a. Those two can subtract. So similarly here, this one is acting as a coefficient of, this one is acting as a variable of 7. Okay, so now what is 7 raised to power 7? 7 in brackets 7 raised to power k minus 7 raised to power k. You have a 6 in brackets, you have a 6 in brackets, you have a 6, then in brackets you have a 7 raised to power k, like that. Now if you check for this statement, if you were to divide by a 6 here, you find that the 6 and the 6 will cancel out. This is just proof enough to say this statement is divisible by 6. So now if you were to try out, put any, since this k, this is just an assumption to say there's an integer which is here on k. So if you were to put any number here, it being 1, 2, 3, provided it's a positive integer, you find that after doing the multiplication here, whatever number you get divided by 6, it will give you an answer that won't leave any remainder. So if you were to put a 1 here, this will be 7 raised to power 1, which is just a 7. Then 7 times 6, that is just a 42. A 42 divided by 6, that one is divisible, it won't leave any remainder. So from here you conclude, you say, therefore, by mathematical induction, we've proved to say 7n minus 1 is divisible by 6. You end there like that. It's done. Thank you.